the correlation coefficient, but not just any correlation coefficient, Pearson's correlation coefficient. But as we just saw with those multiple choice ones, line of best fit is very subjective. But of course, in maths we like precise and exact answers. So there is a formula to work out the correlation coefficient. The symbol for it is, we use R if we're talking about a sample, and we use rho if we're talking about population. It allows us to all get the same, well, for want of a better word, line of best fit. This is the formula to work it out. So you're going to have two random variables, x and y. So you've got two pieces of data. If you want to find this correlation coefficient, you find the covariance, that's what COV stands for, the covariance of xy over, and S of course is our standard deviation. Variance, remember, expected value of x minus the average squared, we can do that. Covariance is this. It's the expected value of x minus the average of x's times y minus the y averages. That, when you expand all that, just ends up being this. The average of x times y, so if you've got all the x values and y values, those matchings, found the average of them, minus the individual averages multiplied together. We should get in between minus 1 and 1. If it's equal to 1, again we're just talking about the size of it here, don't care if it's plus or minus, then that's a perfect correlation. In fact, all those points lie on a straight line. Very rare for that to happen experimentally. Strong, we say, well, between 0.6 and 1 then, that'll be strong. Moderate, 0.4 to 0.6. Weak, 0.1 to 0.4. 0 to 0.1, virtually no correlation at all. And of course, if it is 0, then there is no correlation between the data. If it's a positive one, then that's basically saying as x increases, y increases. It's a direct variation. Whereas if it's negative, it flips. As x increases, y will decrease. Let's do an example of working this out. So we have some data here of different people, 8 people there, their weight at birth, and then again their weight when they were 21. Here are their weights. Construct a scatter plot. How would you describe the association? There's the scatter plot. Well, it's looking linear. It appears to be strong, but as I say, that's very subjective. Well, let's calculate the correlation coefficient and see if indeed it comes out to be strong. I'm going to say x is going to be the birth weight, y is going to be the weight at 21. Let's create our table. There's the x and the y. We'll need a sum column to work out all the pieces of information. X times y, I'm going to need that as well. X squared and y squared, so I can calculate variance. I'll need that information as well. I think is that enough? Yeah. So to find the average of x, go along that line. We've got 22.7, but I've got to divide it by the number of scores, 8. Okay. Now I can do the y's. There's the average of the xy's. Now let's work out the standard deviation, and we get 0.52 for the x's, and the y's we get 3.55. I think that's all the information we need now for our formula. Subbing it into the formula, doing our calculations, we get 0.7862, which was in that range we said for strong. That brings us to the least squares regression line, which is basically the line of best fit that satisfies that formula. Okay? Because if we get an exact one, we no longer call it the line of best fit, because that's our subjective one. We actually say, well, it's a least squares regression line. So fitting a straight line, least squares regression. Now what it's basically doing there, why it's called least squares, is it gets the distance of the point from the line, and it's trying to minimize that distance. But why is it squared? Because I don't want positive and negative, so they square it. So everything's positive, so when you add it together. That's why, go back to junior school, you remember the standard deviation formula you used to use that? And you said, well, why are we finding the sum of these squared and then finding the square root? Well, this is basically why. Because it's finding that distance from the least squares regression line. That's what it's on about. It minimises the sum of the squares from those distances. But the other thing it will do is it guarantees, because we know the average, we guarantee that the line passes through that point. So it's a point that's definitely on the line. Now, the slope will be the covariance divided by the variance of x. That will be the slope of the line, which is, and there's our formula for that. Well, the y-intercept, well, we know y-intercept because y equals mx plus b. So it's b we're trying to find. But we just said that x, y, the average of those is on the line. So therefore, b must be the y average minus that slope we just worked out times the x average. All right, back to our one. There's the line of best fit that I've drawn. And I'm going to find the equation of my line of best fit. And let's see how good I go compared to when we work out that least squares regression line. So I've got to find 2 points on the line. Nicely, my line of best fit happens to go through some nice points here. I know 250 is a point on that line, and the other one I picked, 0.27540. Okay. Slope, 5.7971. Y minus y1 equals m outside of x minus x1. There's my formula, my line of best fit. Let's see how good I do. Find the least squares regression line, and then we'll draw it and we can compare the two, see how good my line of best fit was. So my slope is going to be that correlation coefficient times deviation of y over deviation of x, 0.36. From there I can work out the y-intercept using that formula we just saw, 39.616. There's the equation of the line, 5.36 plus 39.62. There's a point on that line, there's another point on that line, draw it in. It wasn't too bad, but let's see what they've done in the HSC in the past. The very first of this new course, they had this question. A cricket is an insect. See, they tell you everything. The male cricket produces a chirping sound. A scientist, as they do, explores the relationship between the temperature and the number of chirps heard in a 15-second time interval. I'm sure it's useful knowledge. Once a day for 20 days, they collect the data. Based on the 20 data points of scientists, here's the information we've now got from their little research project. They gave us this box plot of the data. They told us that the mean temperature was 0.525 degrees below the median temperature. And a total of 684 chirps were counted. And that was in 20 data points. From that, they fit a least squares regression line. And thankfully we don't have to work it out, they've given it to us. Y is minus 10.6063 plus, well, they sort of gave it to us. They haven't given us B, they haven't given us the coefficient of X, where B is the slope of the regression line. But they've reminded us that that line will go through the point of the average of X, average of Y, and they've even told us what those symbols mean. That was very nice to us. Now for the question. Calculate the number of chirps expected in a 15-second interval when the temperature is 19 degrees, correct to the nearest whole number. So this is one of these questions which isn't scaffold. From memory, I think it was worth 4 marks. You basically had to put everything together. And they tend to be going more that way. We're seeing more of those sort of questions in the HSC now, where it's, no, we're not going to give you part I do this, hence do this. I mean, they still have those. You see more of these, okay, it's worth 3 marks, it's worth 4 marks. You put everything together. Show us what you know. Well, first thing I did was worked out the average. Remember, they told me, let's go back to it, there it is. The mean temperature was 0.525 below the median temperature. I can read off the box plot that the median is 22. So from there, I can work out the average, 21.475. Now, Y average, I can work out, because Y was the number of chirps, and they told me there was 684 chirps in 20 collections, so 34.2. I have those. Now, I know the line has to go through those 2 points, so I can now substitute in and work out B. Therefore, it passes through there, substitute in, we get B is, well, I've left it as that fraction, because remember they wanted to know what it is when the temperature was 19, so now I'll just sub into that formula, and I get 29.03, so 29 chirps to the nearest chirp. What about last year's one then? A university uses gas to heat its building over a period of 10 weekdays during the winter. Gas was measured in megawatts. Do you measure gas in watts? I thought you measured gas in joules. Oh well, megawatts. And the average outside temperature each day was recorded in degrees Celsius. X is going to be the average of the outside temperature, Y is going to be our total daily gas usage, and we've found a least squares regression line. The equation of that line predicted when the temperature is 0, the gas usage will be 236. The 10 temperatures measured to make all this prediction, and there they are, 0, 0, 0, 2, 5, 7, 8, 9, 9, 10. But the total gas usage for those 10 days, 1,840. Again, they've reminded us that in any data set, that least squares regression line will pass through the average of the two, and they've defined those for us. Using the information, plot the average on this grid. They gave them a grid. Let's work out the average. They gave us all those temperatures. There was 10 of them, so we know 5 for X bar. Now Y bar, where did I get that from? Oh, that's right, they told us there was a total amount of gas usage over the 10 days was 1,840. So I simply have to plot the point 5, 184. There it is there. Oh, and the y-intercept. Well, the y-intercept is when our temperature was 0, and did they give us that information? Hang on, where is it? Ah, there it is. They told us that that line predicts that it's going to be 236. So I need to plot 0 to 36. There we go. Interestingly, it doesn't actually say draw the line. It just said plot those 2 points. Well, okay. There's those 2 points. What is the equation of that line? Well, I've got 2 points. It's now really just saying find the equation of the line. Slope, minus 52 on 5. Well, we know the y-intercept is 236, so y equals mx plus b. There is the equation of our line. In the context of that data, identify one problem with using that to make a prediction. When the average outside temperature is 23, we got a problem. What's our problem? Well, okay, what happens at 23? I get the y is negative 16 on 5. Well, there's my problem. Because what was y representing? Gas usage. So we're saying that when the temperature is 23, actually they're going to start giving me gas. Well, that's not going to happen. So what did I say? I just said, look, it's predicting the gas usage, which would be negative. I mean, that's impossible. So that's not going to happen. That's the problem with it. Okay, that shall do us.